Hi everybody, welcome back. Section 32.2 with vectors today. We're going to do some drawing. Getting back to our robotic arm, which I know we really never spoke too much about, but here's the robotic arm. That the base of the arm is attached to the origin, and the first part of the arm, the first piece of the arm, as you can see, is right here. And then the second piece of the arm is attached to that. This process, or the way this looks, is exactly how we will graph them. So if we switch this over, it's not obviously anything too difficult. When we switch this over and drew this graph, or if we put this in terms of vectors, the tail would be obviously at 0, 0, and the head at 6, 8. Which I don't know if I'll get exactly right, but then what happens is the next piece, the one that you draw next, starts right there. So from 6, 8 to 18, 3 is the next vector. We call this tip to tail. So this is what it looks like in vector form, which is, I think, very clean to see, but it's just helpful to understand that that's the process that we're going to graph this, add these, subtract them, multiply them, is tip to tail. So to review component form, vector u, the component form, that's the easy one because it's in standard position. And so from standard position is just the coordinates of the head. So this is 6, 8, or right 6, up 8. That is vector u. For vector v, you can't just use the 18, 3 because that's not component form. Component form is head minus tail. Very, very specifically. X's with X's, Y's with Y's. So component form here is 12, which is 18 minus 6, and then we do 3 minus 8, so negative 5. Or in this case, from this point right here, from this vector head, we went right 12 and down 5, and that's where it goes. Now they want us to, in the next step here, they want us to connect. It says draw the vector from the base of the arm to the end of the arm. What does this vector represent? So this is basically, it's u plus v. It represents an vector u plus vector v, or the resultant. And the component form of this is, of course, 18, 3. Now, I put kind of a lot of answers all right there in that one question, just because I think it's easier to keep track of. But down here in the lower left-hand corner, this is an example of what we're talking about with the resultant. Your solution, your answer, is your resultant. And we're going to go through this a couple more times. So I'm just going to skip the picture. You can look at that if you'd like to. We're not going to draw it that way, so that's basically why I'm skipping it. We're going to continue with our tip to tail method rather than the method they use, which is the parallelogram method. All right, sorry, I'm just trying to get my pencil to work. Excuse me. So take a look at part A. It says add each both geometrically and symbolically. Well, symbolically they just mean with the arithmetic, with the actual numbers. So if we were to add this, give it a name please, vector s plus vector t, and it's just like it feels. Add the x's together and then add the y's together. If we would do this one, vector q plus vector r, add the x's together, so negative 6 plus 8, that's a 2, and then negative 5 plus negative 5 is, of course, negative 10. Negative 5 plus another negative 5. It's not 0. So let me show you what they want you to do geometrically, or what we're going to do geometrically. If you've done this in Alex, it's the same thing that Alex does. If you've done it in physics, it's similar to there too. It's a little bit more basic here, but same idea. I'm going to use this graph paper. I can tell by, I'm doing part A, I can tell by all my parts that and the answer that's probably in the first quadrant. So you start with the first one, and whichever one you're calling the first one, it really doesn't matter. I'm going to call vector S my first one, and you draw your first one in standard position. So from 0, 0 to 4, 1, so we're going to go right 4 and up 1. This is vector S. Now I'm going to label it. It's going to make my picture kind of junky, but I am going to label it. Now, to add vector t, I'm adding from this point right here, from this point where it ends, from the point 4, 1, we're going to do the components. The components are left 3. These are not points. These are components. So left 3, up 4. I'm just going to count the squares. And that puts us right there. That puts us at the point, of course, 1, 5. We already knew that. This is vector t. Now, what we draw in last is the resultant. And the resultant comes from the origin, and it goes to where the second head was drawn. So essentially what happens is you should end up with 2 arrowheads pointing to the same point, and that point is your solution or your sum, your answer. And so this picture and the numbers should match, and they do. We're at 1, 5. We thought we were going to be at 1, 5, so it's all good. Now with subtracting, we can't just subtract a space. Vectors are like adding the space. We make the space bigger, change the shape, change the size of the space. So we can't just get rid of it. So instead of subtracting, we're going to do what's called the additive inverse. The additive inverse is a fancy way of saying it an opposite. So an additive inverse is the exact same thing as an opposite. A multiplicative inverse this is a reciprocal. In case one gets you thinking of the other, because you've heard these words before. It's probably been a while, but we are concentrating on additive inverses right now. So the additive inverse for vector w, the way you would write it is the opposite of vector w. That's what it looks like. So that's how you would read it. If you want to call it negative vector w, it makes more sense really to say opposite, because we want to take the opposite of everything inside here. So the opposite of that would be 2, negative 5. And then, of course, the next thing we're going to do is subtract these vectors graphically and symbolically. And they're going to call it symbolically, which is weird because it's just the numbers. So we're going to take a look at number 9 here. And number 9 uses from number 8, which is a little bit awkward. So it says we want us to add vector v. Just so we have the coordinates here, vector v, or the components, is 3, 4. And vector w, I know we just did the opposite, vector w is negative 2, 5. And of course, by the notation, you can tell these are the components and not the points. So we're going to do this to do subtracting, because they want us to subtract vector v minus vector w. We are really going to think of this as vector v plus the opposite of vector w. It is the second one that you do the opposite of. So for vector v, we're going to go over 3 and up 4. Connect that to 0, 0. So there's vector v. Remember, we go tip to tail. So where that one ended, which is the 0.34, we're going to start the next one. But we want to do the opposite of vector w. So the opposite of vector w, if you recall, if we need to go through it again, is 2, negative 5. So from this point right here, we're going to go right 2 and down 5. And that puts us right here. And then you draw your answer. The answer is the resultant. And the resultant comes from 0, 0. And you should have 2 arrowheads pointing at the same spot. Now, when you go to give your answer, obviously we have it a couple ways. You can do the numbers, and you might be more comfortable with the numbers, or you could read the graph. This is the point, 5, negative 1. And that is, of course, the answer, 5, negative 1 in component form. So the resultant's components, or the components of the resultant, the answer, is the answer to the question, whether it's on the picture or whether it's the number. So because this is a little bit different, we're going to do this again. Go through it one more time. Also, what happens with these is the pictures become pretty awkward looking, especially if the triangles are super obtuse. And you just have to be kind of careful with how you draw your lines. The grids in the book are pretty good. So we'll take a look at 12a. So it says to subtract each pair of vectors, both geometrically and symbolically. And again, symbolically, as you know, means with the numbers. So I'm going to do that one first. Sometimes it's obviously better because you'll know what the answer is before you actually graph it. So we're going to have vector S, which is -2, 2, plus the opposite of vector t, which I'm just going to write as the opposite here, -1, 4. So vector S, don't change the problem, it's still minus vector t, even though I kept a plus sign there, is -3, 6 in component form. So that's our answer. Now to actually do this graphically, we're going to start with vector S. I'm going to start with the first one first, and order in subtracting really matters. So you've got to start with the first one first. So we're going to start with -2, 2 as our original vector. Now we're going to add the opposite of vector t. So the opposite of vector t is, I have it written there, -1, +4, which means left 1, because that's in the negative direction, and up 4. And so this is the part where I try to warn you, it gets a little bit awkward because the picture gets narrow. So this is the opposite of vector t. Now your resultant comes from 0, 0 and goes to where that other arrowhead is. So there should be 2 arrowheads or 2 tails, or sorry, 2 heads of vectors pointing in the same exact spot, which of course would coincide with our solution, which is -3, 6. The last operation we're going to do with this is multiply. We do not divide vectors, which is kind of nice, so you don't have to worry about dividing these spaces or this idea of this shape. When you do multiplying, you are multiplying by what's called a scalar. And so a scalar it looks like distributive property. It is. So to graph it, if you look down here in this lower right-hand corner, to graph it, you can see you just basically go tip to tail, and you'll end up with just a longer segment, and it'll just keep going however many times you need to do it. So we're going to do some of this. It looks like distributive property. It is distributive property. So on 2a, to take 2 times vector v, we would just multiply or distribute a 2 through the entire vector. So 2v, leave it in component form, is going to be -4, 8. 3 times vector w will be -9, -3. -2 times vector w is just what you think it is. Distribute a -2. And so we would get 6, 2. Now, to draw the graph, I'm going to draw the graph of the last one, the one that's got the negative sign in front of it, just because I think that's the weirdest one, and one that you don't currently have an example for. So for graphing the opposite of vector w, basically we're going to do it 2 times. So I'm going to break this down a little differently. This is the opposite of vector w, but we're going to draw it 2 times. Not equal, but this is how many times we're going to draw it. So the opposite of vector w is 3, 1. And so for this, we're going to go right 3 and up 1. That's opposite of vector w. Then, since we have to do it 2 times, we start from there and you do it again. The exact same thing. Right 3 and up 1. Now, even though there aren't 2 different vectors forming a triangle, we still have a resultant. The resultant is basically kind of superimposed on top of all of this, and so our resultant is that basically one vector, or that single vector, that ray if you want to call it, and it does point to our solution, which is 6, 2. Your assignment is here on page 449, and we're going to do today 15 through 20 on page 449. Make sure you're keeping these answers, keeping your homework somewhere where you can find it, because you will be asked to give me some of those answers when we come back from spring break. I hope you have a great spring break, and stay safe and be smart and continue to do your work.